Hi, I'm Nail, and we'll be discussing the division algorithm. For all integers a and b, with a not equal to 0, there exists unique integers q and r such that b equals a times q plus r, and r is greater than or equal to 0 and less than the absolute value of a, where b is the dividend, a is the divisor, q is the quotient, and r is the remainder.
Hi, my name is Ethan, and I'm going to be doing a proof on the division algorithm. So first we want to show existence. So then we have a and b as integers such that a is not equal to 0, and we're going to suppose that a is greater than 0. And we're going to consider this set b minus ak, where k is an integer, and b minus ak is greater than or equal to 0. And the reason why we want to consider this set is because from the division algorithm we have b is equal to aq plus r, and all the elements are just the rewritten form of the remainder r. So then we first want to show that S is non-empty. So we have two cases: b is greater than or equal to 0, and b is less than 0. And for time's sake, I'm not going to cover this, but we basically show that S is non-empty. And now we use this statement here: a non-empty subset of integers that is bounded below by an integer has the smallest element. So we show that S is non-empty, and we also know that S is a subset of integers because b, a, and k are integers, and this would be an integer. So then we know that S has the smallest element. And this statement is derived from the well-ordered principle, which states that every non-empty subset of natural numbers has a smallest element. So we use this statement derived from the well-ordered principle to show that S is the smallest element, and then we use this smallest element to show existence of Q and R. So we call R as our smallest element, and since R is in S, then R must be equal to b minus aq for some integer q. And we also know that it must be greater than or equal to 0. And then we can actually rewrite it to fit our form in the division algorithm. So b is equal to aq plus r. And now we want to show that r is less than the absolute value of a. And since a is greater than 0, then we can just show that r is less than a. And now we're going to suppose for contradiction that r is greater than or equal to a, and we're going to consider b minus q plus 1 times a, and this is equal to r minus a, which we know that is greater than or equal to 0, and we know that this is the element of S because it's greater than or equal to 0, but we actually know that it's less than b minus a times q, which is a contradiction because this is the smallest element of the set, and we found another element of the set that's smaller than it. So now we have that r is greater than or equal to 0, and r is less than the absolute value of a. So then what we did here was that we showed that there is a q and r that are integers such that b is equal to a times q plus r, and r is greater than or equal to 0, and r is strictly less than a. And then in the next section, I'm going to show uniqueness. So now that we show existence, we're going to show uniqueness of q and r. Let a and b be integers, and a is not equal to 0. Suppose that there exists q1, q2, r1, r2 that are integers, such that these conditions are fulfilled. And then without loss of generality, we're going to assume that r2 is greater than or equal to 1. And then from these conditions above, we can set these two equal each other. And then we can conclude that a divides r2 minus r1. And then since we know that r2 minus r1 is in between 0 and the absolute value of a minus 1, we can conclude that r2 minus r1 is equal to 0 because it cannot be any other number because there's no multiple of a between 0 and the absolute value of a minus 1. So from that, we can conclude that r2 is equal to r1, and then we can also show that q1 is equal to q2. And then we can conclude that q and r are unique.
Okay, so for example 1, we'll have divisor a be greater than 0 and dividend b also be greater than 0. let A equal to 8 and B equal to 30. To compute Q, we can take the floor of 30 divided by 8, and we'll get 3. And to get a remainder R, we do B minus A times Q, we get 6. So we have found unique Q and R values given A and B. And then down below, we show that we have fulfilled the requirements of the division algorithm. Let's do another example, but except where B is less than 0. So A will still be 8, but this time B will be negative 20. To find Q, we can do negative 20 divided by 8 and take the floor of that, and then we get negative 3. And then using the same method, we can find R, and then for that we get 4. And down below, we show that we have fulfilled the requirements of the division algorithm.